Hello, I welcome you once again to my YouTube channel, and today I'm going to be taking you through just a simple problem that you see on my screen here. Have you ever made this and you feel it's a little hard for you? The answer is it is actually not hard to have this done, and I request that you follow me through simple steps that can take us to this result. As the question says, show that integral of sec x with respect to x equals ln of sec x plus tan x plus a constant of integration. Now, what you need to do here is to first realize right away that we're going to apply the substitution t equals to tan x out of 2, or using the t formulae. And from here, I will first need to say that integral of sec x with respect to x is just as good as integral of 1 out of cos of x dx. From here, we can say this is integral of 1 divided by, now cos x can be written as cos squared of x out of 2 minus sine squared of x out of 2. That is from the idea of double angles and half angles. Now from here, we can directly divide through up and down by cos squared of x out of 2. That means when you get 1 divided by cos squared of x out of 2, we shall get sec squared. Sec squared x out of 2 divided by cos squared x out of 2 divided by the same term shall get 1, and then minus sine squared x out of 2. If you divide it by cos squared x out of 2, you will get tan squared x out of 2 with respect to x. Now from here, we can clearly see that this can be modified to integral of 1 plus tan squared x out of 2 divided by 1 minus tan squared x out of 2 with respect to x. Now from this stage, we can comfortably let let t equal to tan x out of 2. And if t is tan x out of 2, it means dt dx now becomes a half sec squared x out of 2. Should we make dx the subject, dx becomes 2 dt, ideally divided by sec squared x out of 2. But remember, sec squared x out of 2 is the same as 1 plus tan squared x out of 2. So that means I will comfortably write this as 2 dt divided by 1 plus t squared. Why? Because tan x is clearly called t. We let t to be tan x. So where there is tan squared x out of 2, I call it t squared. Now from here, we can do the substitution. We can now say that it means our integral of 1 plus tan squared x out of 2 divided by 1 minus tan squared x out of 2 with respect to x is just as good as integral of 1 plus t squared divided by 1 minus t squared, but then we are multiplying everything by dx, which became 2 dt divided by 1 plus t squared. So you clearly realize that 1 plus t squared is cancelling out. So we remain with integral of 2 divided by 1 minus t squared with respect to x. When you realize that now we have this, you can easily know that the denominator, which is 1 minus t squared, can be written as the difference of two squares. So because it can be written as a difference of two squares, we can say Now our integral becomes 2 divided by 1 plus t into brackets 1 minus t with respect to t. Now from here, clearly this is a partial fraction, particularly type 1, where we have a denominator with only linear factors. So I will say let 2 divided by 1 plus t into brackets 1 minus t be equal, or we can use an equivalent sign, to a divided by 1 plus t plus b out of 1 minus t. So from here, the LCM of the right hand side is the same as our denominator of the left hand side, and therefore they cancel out, giving us 2, which equals to a into brackets 1 minus t plus b into brackets 1 plus t. So from this, we can clearly see that if we substitute for t equals to 1, I'm using up the cover up method. If I consider the first factor equating it to 0, you get t equals to 1. What comes out is that now we shall have 2 on the left hand side is equals to 2b. Why? Because I've put a 1 here. For this, the whole of this becomes 0. That means practically the value of b becomes 1. Now after saying this, we can also do the same. We can substitute again. We can substitute t equals to -1. Where did I get it from? By equating this factor to 0. That means clearly that 2 is going to be equals to, that is going to be 2a. Why 2a? Because when you put -1 in the place of t here, you will get 2a, and the other one becomes 0, meaning the value of a is also 1. That means we can now conclude that actually 2 divided by 1 plus t into brackets 1 minus t is actually equals to 1 out of 1 plus t plus b, which is also 1 out of 1 minus t. That means now the integral of 2 divided by 1 plus t into brackets 1 minus t with respect to t is just going to be as good as integral of 1 out of 1 plus t with respect to t plus integral of 1 out of 1 minus t with respect to t. Now, the first integral gives us a natural log of 1 plus t, and the next integral gives us a negative natural log of 1 minus t, and then plus a constant of integration. Now you realize the actual integration is done, but we now have to bring in the trigonometry to get the answer we want. But before we bring the trigonometry, we need to appreciate that this can be written as natural log of 1 plus t, but remember t is tan x out of 2, divided by 1 minus t, but t is tan x out of 2. And then from here now, we can bring in the trigonometry. So we need to remember that tan x out of 2 is the same as sin x out of 2 over cos x out of 2. That's what I'm going to use. So it means we shall have a natural log of 1 plus, now this will be sin x out of 2 divided by cos x out of 2. All this, we need to now have a bigger bracket, divided by 1 minus, again, sin x out of 2 divided by cos x out of 2. Something to appreciate in this expression is that the denominator and the numerator will have the same LCM. And so at the end of the day, when we go to the next step and try to simplify, something will easily cancel, as we shall see. Now, from here, we can clearly see that we shall have a natural log of, when you take the LCM for the upper part, it is cos of x out of 2. That means we end up with cos x out of 2 plus sine x out of 2, then divided by, I just look at the denominator now. I look at the denominator now, which will give us, again, cos x out of 2, because its LCM is cos x out of 2, and then minus sine x out of 2. What has happened here is that the LCM for the numerator has cancelled with the LCM for the denominator. Then from there, we can now think about rationalizing what the function we have currently here. So the best option will be saying this is natural log. Now we have quite a bigger space. Cos x out of 2 plus sine x out of 2 in out of cos x out of 2 minus sine x out of 2, and then we multiply by the conjugate of the denominator, which is going to be cos x out of 2 plus sine x out of 2, divide everything by cos x out of 2. Remember, we're not changing the meaning. That's why I'm multiplying by the same function up and down. So when you look at that, the upper part particularly clearly tells us that this by this will be one of the brackets but squared, which gives us cos squared of x out of 2 plus 2 sine x out of 2 cos x out of 2, then plus sine squared x out of 2. Then the denominator is the difference of two squares. Remember, we have a natural log, don't forget that. So for the denominator, we have a difference of two squares, which is going to give us cos squared x out of 2 minus sine squared xc out of 2. Now remember from trigonometry that cos squared x out of 2 plus sine squared x out of 2 is 1. That means we can comfortably say this is already 1. Natural log of 1 plus, and then 2 sine x out of 2 cos x out of 2 is just the same as sine x from double angles and half angles. Then all this divided by cos squared x out of 2 minus sine squared x out of 2 is just the same as cos x. It is the same as cos x. And then you realize that actually, I beg your pardon for sine x out of 2 that I've written here. It's supposed to be just sine x, not sine x out of 2. So you realize that now, clearly we can see that we can say 1 over cos, which is sec. So we shall say ln of sec x. And then sine over cos is tan. So we get our answer that we wanted right away from the start. But don't forget that we should have had our constant of integration all through without forgetting it out. Don't forget it out because you are integrating. So you make sure you maintain it all through because we didn't have limits for this. So this brings us the end of this integral. And so we can now conclude therefore that indeed our integral of sec x is clearly ln or natural log of sec x plus tan x plus a constant. As simple as this. When you go off this, please make sure you subscribe before you go off because you need to receive notifications for the next videos that will make your life so easy to proceed with us. Grow yourself mathematically. See you in the next video or next tutorial.